Swayam Prabha. Digital India. Educated India.
Okay, welcome again to this video lecture series on basic surveying. Today we are talking about the module number 5, which is on theodolites and total stations. We have already started this module in our last lecture. So today our lecture is lecture number 2 of this module. Now this is the structure of all our video lectures where we are talking at this place. Now what we have done so far as far as the theodolites and total stations or this module is concerned. Today we are going in the other part of it. We will start with the telescope, how it is constructed, what is there inside, what kind of telescope it is. So we will look into this telescope which is used in the theodolite. Then we will see some more definitions which we need to know in order to go further while we are reading about the theodolite. Then we will see some temporary adjustments of a theodolite. These are setting, leveling, centering and focusing. And then finally we will see how we can make use of this in order to measure one horizontal angle. So this is all we are going to cover today. Now to start with the telescope. What the telescope is? This telescope is Kepler's type telescope. Because you must have done in your physics classes that there are different kinds of telescopes. This is Kepler's type telescope, and as you can see here, now we have seen yesterday in our last lecture also, this is the objective lens, that's the eyepiece here. Now how it functions? The object is somewhere here on this side. The rays from the object are passing through the objective. They are creating an image somewhere inside. Now this image is brought into within the focal length of this eyepiece or this lens here, and this is how the image is generated, the final image which you observe. Now we will see the line diagram of this. So to see the line diagram, here in the slide you will see that AB is an object. From this AB, that's our telescope, and the telescope means this is the objective lens and this is the eyepiece. The rays from the object, they will form the image of the object somewhere here. So this is the image of the object A dash B dash for the object A and B. It's a simple line diagram which you know from your basic optics. Now this A dash B dash is placed inside this telescope in such a way that it is within the focal length of eyepiece. Now why is it done? It is done because this is the focal length. This distance is the focal length of eyepiece. It is done in order to ensure. Now what will happen? If it is within the focal length, how the image will be generated? Now these rays will go here. Similarly, they will meet at the focus. Now the rays from here passing through the optical center will go like this and will go like this. Now these rays, they do not meet on this side, rather they converge or appear to be converging on this side. So finally we will have the image formed here, and this is how the image is formed, and this is how the image will look like. So for the observer, if the observer is here, he is looking through the eyepiece, what he sees, he looks at A dash, A double dash and B double dash, which is not the real image. It's not the real image. So this is actually the line diagram of Kepler's telescope, which is mostly used in our theodolites. There may be some extra lens, additional lens, which will invert this image, because at this moment the image which you are seeing for your ranging rod, you are seeing the ranging rod inverted. Though it doesn't matter for an experienced surveyor, it is alright. He knows that how the image is generated and he knows how to take the observations. But in order to expedite the survey, in order to avoid this kind of confusion, the modern instruments are fitted with some extra optics in between, extra lenses, and they will further turn it and the image will look erected. It will look erected. Now, some definitions here about this Kepler's telescope. Now, some of the terms. Over here, where our imaginary image is being formed, this place we have one additional assembly which we say a diaphragm. Now, what is this diaphragm? A diaphragm, if I draw, it is a glass sheet, circular in shape, and it will have some wires. Sometimes these are the wires, or sometimes these are the, on a glass plate, some marks etched on it. So, for example, this is one example of the glass sheet or glass plate on which some marks are etched. Now, this assembly we say diaphragm or cross wire. There may be various kinds of these depending the instrument, or maybe depending on the instrument. All these facilitate proper bisection, all these facilitate proper taking of some observations. So, when we look through the telescope, what we see, when we look through the telescope, for example, if I have focused this telescope on a tree, let us say, so what I see the tree, and my telescope is focused on this tree over here. That is the field of view. I cannot see beyond this. I can see only this part. That is the field of view of the telescope. Now, in this field of view, I will see my cross wires, depending what kind of arrangement is there of the cross wires. Okay, let us say this is the arrangement. So, this is how, when we look through the telescope, it looks like this. Now, here in this case, this particular point, if I, this center of here, this particular point is the center of cross wire, because this is cross wire and this is center of the cross wire. Whenever we sight through the telescope, our line of sight is defined by this cross wire, because we are bisecting anything with the cross wire. You see the cross wire, you see the object, and you ensure, yes, now this is my line of sight. So, the line of sight in the telescope is defined as you go here, somewhere here, as I was telling you, that we have the cross wire or diaphragm. This cross wire is fitted here, over here. So, the point center of the cross wire and the center of the objective, joining these two, the line formed is called the line of sight. Okay. Now, another definition, that is of line of collimation. Now, what is this? This is something of the telescope. This is also called axis of telescope. Now, what it is? Here, a line joining the center of the eyepiece and the center of the objective. If I join these two, then the line which I get is the line of collimation or axis of the telescope. Ideally, these two lines, the line of sight and the line of collimation, should be same. This is how the instruments are made, but they may be slightly in error also. They may be not constant. So, that is the line of collimation. So, we have seen the cross wire, the line of collimation, the line of sight. Well, we go further now. Okay, two more definitions. In those definitions, we may have an external focusing telescope or internal focusing. internal focusing telescope. Now what this is? Now in this case, when I focus the object, what I do, I use the focusing screw here, and I see, when I sight through the eyepiece, I see the things are focused. Now what is happening basically in the case of the focusing? If you look at the line diagram again, we have the eyepiece, we have the objective. Now the focusing means somewhere here is the cross wire. Okay. Now this cross wire is clearly seen by this eyepiece. This eyepiece is placed at such a distance from the cross wire that we can see the cross wire very distinctly. We will talk about that in a moment. Well, what we want, because this cross wire is our frame of measurement, reference of the measurement, we want to bring the image which is formed from here on the plane of the cross wire. So we want to bring the image here, this A dash and B dash, and then once this image is magnified, the cross wire is also magnified accordingly. So both image and the cross wire both are magnified by the same amount. So focusing this objective means bringing the image which is formed by the objective there at the plane of the cross wire. Now how can we do it? Let us say the very first image which is being formed is somewhere here, A dash and B dash. Now we want to bring this image over here, so we want to shift this image by this much distance. So what we need to do, we need to shift this lens by equal amount. So this lens needs to move, the objective lens needs to move in order to focus this image on the crosswire plane. Now how it is ensured? This could be ensured. Let us say in one case, we have a telescope where we have two tubes, and that's the objective, and somewhere here is the eyepiece. Okay, we have a gear mechanism, and using this gear mechanism, this tube moves inside or outside. So what is happening now? We are changing the location of the image inside the tube as desired by moving this tube inside or outside. So this kind of focusing is called external focusing. Now in the case of the internal focusing, because there are some problems with external focusing. What the problems are? Problem is, well, if the center of the instrument is here, now this tube starts moving here and there, so the balance of the instrument will change. Then there is a moving part, more chances of the errors, more chances of this getting disoriented. It is all aligned initially, but this might come down because of its weight after some time. Then this part which is coming out of the tube is exposed to the dust. So there will be a lot of dust in the telescope. So because of these reasons, this external focusing telescope is not used anymore. Most of the instruments which you find now will find of internal focusing type. What happens in the case of the internal focusing? Now our eyepiece is somewhere here, and that's our body of the telescope, and at the end of this body is the objective. Now here in this case, these two, the objective and the eyepiece, they are fixed. They are fixed here. Now if it is fixed, how to obtain the desirable thing? Moving this image, because there is an image formed by objective A dash and B dash, and we want to move this image here and there. How to reach at that? For that there is an extra lens. An extra lens is fitted inside, and now there is a gear mechanism, and this gear mechanism will move only this lens here and there. So because of the movement of this lens, now our image will move here and there. So now what is happening? There is no tube coming out of the telescope. So the balance of the telescope is maintained. So as we see in this case, in the case of the theodolite here, if I focus the objective, there is no change in the length of the telescope. So you can now very well guess what kind of telescope it is. There is no change, nothing is coming out of the telescope. So this is internal focusing telescope. Okay, having done this, now we will go for more important thing. No, that is called, we want to measure an angle. Angle measurement using a theodolite. What are the steps? What all we need to do when we want to measure the angle using a theodolite? There are various, it looks very simple, but there are so many steps involved, and that will control the accuracy of the angle that we will measure. What are those steps? These steps generally we write as temporary adjustments of a theodolite. What these temporary adjustments are? Well, I will give you a problem. For example, let us say you want to do a traverse, and in this traverse you have an EDMI, you are using the EDMI to measure all these lengths. You want to measure all these angles now using the theodolite. Now in order to measure these angles, if it is A, B, C, D and E, we already know why we do the traverse, what kind of uses a traverse can be put to. We know that already. Okay, let us say our our theodolite is at point B over here, and we want to measure the angle A, B and C. This angle is required. So what all should we do? And once we have measured the angle at B, we will move our instrument to C in order to measure the angle BCD. So again, what all we need to do before we start measuring the angle? Is it not that we can straight away carry the instrument, put it somewhere near the B and start measuring the angle? No. We need to do some steps before we can take actually the angle measurement. And those steps which we repeat at each station, B, C, D, A, E, all the stations, these are called the temporary adjustments. Now what these temporary adjustments are, we'll start with number 1, setting. Number 2 will be leveling. And number 3 will be centering. And number 4, focusing. So what all these are, we'll now look into these one by one. Though some of these are dependent on each other. So if you do leveling, we have to do a centering after that. Again, after doing centering, we'll have to check our leveling. Again, after doing our leveling, we'll have to check our centering because they are dependent. Now, what all these are and how we proceed with this is what we are going to see now. And the problem is, we want to measure an angle, let us say A, B and C. This is the angle which we want to measure, the horizontal angle. A, B and C. So naturally, first what we will do, we will come near to this station B. Now when I say B, you can see the B here in the drawing, but please think of the ground outside your room where you are seeing this video lecture. Think of that ground, think of a point at that ground. How that point will be identified? Well, what you have done, because the traverse stations, when we say traverse stations or the survey stations, what do we do mostly? There in the ground, we have decided, okay, we are going to take a particular point as a traverse station. Generally, we will put either a concrete block, and in this concrete block, there is an iron nail which marks the center of the station. So in the plan, it might look like, if this is my concrete block, that's the concrete block, and there is a nail, and the center of that nail is the station. So you can locate that center physically there. All these points the traverse stations are marked like that on the ground. Or maybe if you are doing a temporary work, what you can do, you can take some paint, and using the paint you can draw some lines there on the ground. Okay, my stations. So these are the lines which mark the point. And basically now the job is, when you are occupying here, you want to put your instrument over these points. And this is how you can measure these angles. And this is why we need to do all these temporary adjustments. Now in these temporary adjustments, we will start with one about the tripod. What we need to do with the tripod. Okay, so here we are. Maybe we are in the field now, and we are over that point B at which we have to measure the angle. So the B point is somewhere here in the ground, and you know how that B point is marked. That B point is marked like this, maybe by paint, or maybe on top of that iron nail that we are talking about. So the point is marked there in the ground. Now what my job is, because I need to measure the angle A, B and C, so I want to put my theodolite in such a way that the vertical center or the vertical axis of the theodolite passes through the point there in the ground. Because the center of the theodolite means where, when I rotate the theodolite in horizontal, okay, when I rotate it, it is rotating about an axis. That's the point which is the origin about which we are measuring all the angles. So I need to bring that vertical axis of the theodolite over that point. And our theodolite has to be vertical. At the same time, the horizontal plate of the theodolite has to be horizontal. So well, I occupy this point. Now when you occupy with this point, you start with a tripod. A tripod, as you know, as we can see here, now in this case we can change the length of the legs. We all have the arrangements, and by this you can change the length of the legs. The idea is, we want to keep the length of the legs or the height of the tripod in such a way that after keeping the theodolite on this, the eyepiece should be at my eye level. So we know approximately, well, that's the height of my theodolite, and that's where the eyepiece will be. So this is how I decide about this particular height. The next, what we do, first of all, we center this tripod. How do we center it? We can make use of, if you don't have a plumb bob, you know the plumb bob? If you don't have a plumb bob, I can make use of even a stone. I can drop that stone from the center of the theodolite, whether it drops nearly around that point in the ground or not. If you have a plumb bob, I can suspend this plumb bob like this, and it will tell me whether this particular point is exactly over that point or not. So all these things can be ensured. Now having done this, next I want to, because this is approximate centering, it's not exact centering as yet. Now to do the exact leveling and centering, what we are going to do, then I observe the head of the tripod. That's the tripod head. I want to ensure that this tripod head is level, because this is required. I will put my instrument on top of this. I will need to make my instrument horizontal. The horizontal plate of the instrument should be horizontal. So before I do it in the instrument, I should ensure that my tripod head is horizontal. So how do we ensure it? It's by visual examination. Now there are two movements of the tripod legs. One, I can move the tripod leg circumferentially. Basically, when I move it circumferentially, what happens? It will change the leveling. It will not change the centering. So if I move it circumferentially like this, generally the centering of the tripod will not change much, while the tripod head will change its leveling. So I can do it for any of the three legs depending the requirement. Or maybe I can shift the tripod leg radially outward. Now when I shift it radially outward, what happens in that case? In this case, the leveling of the instrument will not change much, or the leveling of the tripod head will not change much, while the centering will change. So what is our aim when you are working with this tripod? Our aim is, we want to approximately center it, approximately level it, and by using these legs, the movement of the legs, I gave you two movements, radial and this radial movement and the circumferential movement. By doing this, also maybe at times by changing the length, you want to change the length of this leg a little bit instead of giving it a radial movement. So you can do that. So finally what we will achieve our tripod is approximately leveled. Is eye judgment. Just by eye judgment you can ensure it, and as well as it is also approximately centered over that point. Now at that stage we will bring our theodolite and put it on top of this. So one more thing here in the tripod head which is important is, if I show you like this, we have an assembly which can move. So once I bring my theodolite, I can put my theodolite in such a way that it goes into this bolt. So this is the bolt for the theodolite. Now I can bolt it into the theodolite bottom. Now having done that, to do some fine centering of the theodolite, we use this, and this assembly is called centering head. So I can move it like this and just relax it and move it like this, and that will do my leveling centering very accurately. So this is the centering head. So we make use of this centering head. The theodolite is put, just rotation of this, and fine centering is achieved. So we'll talk about this again later on. Okay, now our theodolite is on top of the tripod. We fit it. Now what is next? Next step is leveling of theodolite, because so far our tripod head is leveled and centered. Well, how to do that? Well, for the leveling of the tripod, we have 3 leveling screws, as you can see here, 1, 2 or 3, and these are also called foot screws. Now how do we level it, and what is the purpose of it? Purpose of the leveling. The purpose of leveling is, we have the horizontal plate here. You know the horizontal plate, and on this horizontal plate, using the index, we are measuring the angles, as we have seen. We want to make this horizontal plate truly horizontal. Why we want to do it? As we have seen, if there are 2 objects, we want to measure the angle between these 2 objects. What the meaning of the angle is? The meaning of the angle is, we want to measure that angle on the horizontal plane, not on the inclined plane. So if there are 2 objects here, for this theodolite, one here, the theodolite may bisect like this and bisect like this. We are interested in the corresponding angle at the horizontal plane, the projected angle on the horizontal plane. So our measurement or the graduated ring has to be horizontal for this purpose. Now how to ensure it? In order to do that, we have a bubble tube here, and we have seen what the bubble tube is, what we want to achieve using the bubble tube. Now in this bubble tube there is a bubble, as we have seen in the diagram also. If I look at that from the top, it may look like that's the bubble. Now there are some graduations also. Basically this bubble needs to come to the center. Center means it should be, if it is leveled, it should be here in the center, this way. So the bubble needs to be moved on this side in order to make this bubble tube leveled. And we have seen this thing already, that the bubble is a part of a large circular tube. And why it is so? Because then only the bubble will be formed, and then only with the movement of the bubble tube here and there, the bubble will move here and there, and at the time when the bubble is in center, for example, that's my tube here, the bubble is in center. At that time, if the bubble is in center here, at that time this axis of the bubble tube will be horizontal. So this line will be horizontal. Well, you can think of the axis of bubble tube, an imaginary line somewhere here. That's the line. So this bubble tube is fitted to the instrument in such a way that this line is parallel to the horizontal plate. So in order to make my horizontal plate horizontal, or this lower plate horizontal, what I need to do, I need to make this line horizontal. Okay. Now there may be a case, for example, just think here. In this case, if this black pen is the bubble tube, right now the bubble tube is horizontal, but how about this plane? This plane is not horizontal. This plane will be horizontal only in this case. So there may be cases when the bubble tube is in center. Okay, right now if I see the bubble tube is in center, but we are not sure whether the plate is horizontal or not. So we have to follow a particular step, particular strategy in order to ensure that this is horizontal. What that strategy is, first of all, we put this bubble tube along 2 foot screws. So this is the bubble tube, the axis of the bubble tube, and these are the 2 foot screws. Now I give the rotation to these 2 foot screws either inward or outward together. Either inward and outward together means if these are the foot screws, number 1, number 2 and number 3, and the bubble tube is kept right now this way parallel to these 2 foot screws. That's the axis of the bubble tube. So then these 2 bubble tubes are given either inward rotation or outward rotation. Together, the rotation should be same, either inward or outward. Why is it done? If I give one outward, one inward, then they nullify each, effect of each other. And this is how, what is happening, either this bubble tube is going up or going down, because this is what we need to do. That's the bubble tube. I need to either raise it or lower it in order to ensure that this comes to the center. Okay, by doing it, the bubble tube comes to the center. Next, this is the case. What we have achieved a case like this. A plane, there may be a plane. For example, let's say we start with a horizontal plane. This is a horizontal plane. Now for this horizontal plane, I can give it 2 rotations. One in this plane, it is inclined, but again, all these lines are horizontal. Then second rotation, what I can give in this way. So these 2 rotations combined together will form one rotation, second rotation. So initially our horizontal plate may be like this. So what I need to do, I need to make it horizontal first this way, then this way. So in order to do this, what I am doing now, I keep my bubble tube in this direction of the third one. What is the meaning of this? I rotate it, the bubble tube is rotating now by 90 degrees, and it's along this third screw. That's the bubble tube, that's the third screw. Now I rotate the third screw, only the third one. Now what is happening? The bubble tube is either going this way or that way, so that it is in the center. Now once it is in the center, what we have achieved? Starting from a plane like this, we first made this line horizontal. Okay, this line is horizontal now. Then what we ensured? We made it horizontal this way. So if this is horizontal, this entire plate is horizontal. So this is what we achieved by putting this bubble tube in these 2 perpendicular directions and using these 3 foot screws. This is how the instrument is made leveled. Now after the leveling, because the leveling will change the centering a little bit, again we need to ensure using the plumb bob whether the centering has changed or not. And we again need to center it correctly. So we will make use of the centering head as we saw in the tripod. Okay, after doing this leveling, as we are saying that we will center it again. Now this process of centering and leveling will need to be repeated time and again till we achieve where both of them they converge. Okay, the centering is not changing with the leveling, or centering has been achieved as well as leveling has been achieved, because they are dependent operations. So we will need to repeat these. Now this centering can be done by plumb bob as we saw. Now one thing, in the case of the compass, do we need centering or not? Yes, we need to do the centering, because in the compass also you wanted to put it at a point, you wanted to observe the bearings of the lines at this particular point. Yes, we need centering. But in the case of the compass, because the least count of the instrument is very poor, it's not very accurate instrument. So generally we go for the centering just by using a stone. We drop a stone from the center of this compass just to ensure whether we are on the top of that or not. If you want to be accurate, we can go for the plumb bob. So the centering can be done in very, very rough cases using a stone. You drop it and it will fall over that point. Using plumb bob, which gives you accurate centering. There is one more method. optical plummet, because in the case of the plumb bob there is a problem. If there is lot of wind movement, it's very windy weather, and you are doing the surveying in the windy weather, because surveying means you are working in the field. You have to work on those conditions of the field. So it is very much windy. Your plumb bob cannot be centered very easily. So you have trouble. So in that case we go for an instrument which is called optical plummet. What is this optical plummet? If I draw the line diagram of that, it's a very simple instrument. It may look like this. Now here we have a prism, and this prism role is whatever the rays are coming from here like this, it will transfer them, and here is our eye. Now this is the point in the ground. Now this instrument, here in the case of the theodolite, for example, if it is fitted with an optical plummet, so what we will do, in the case of the theodolite, with the optical plummet, this end here in the diagram is looking towards the ground. So this end is looking towards the ground, and there in the ground we have a mark which is for the station. So if I look through this eyepiece here, eyepiece of the optical plummet, what should I see? I should see this mark. Now here in the eyepiece of the optical plummet, again we have a cross wire. So the cross wire of the optical plummet, which may look like this, and the mark there in the ground. Let's say the red line indicates the station there in the ground. This is the station. What our job is, we want to align these 2 points, point A and point B. Point A is the center of the cross wire here. Point B is the center of the mark there at the station, and we want to align these two. Of course, the condition here in this case is it should be vertical. So if it is vertical along the gravity, and if it is horizontal, because this optical plummet is fitted to the instrument in such a way, it is horizontal, so this is vertical, and if it is just exactly over this point and we see these two A and B aligned, so our instrument will be centered. Also, this vertical axis of the optical plummet is also the vertical axis of the theodolite, because now you can see the vertical axis. The axis about which I am rotating my theodolite is the vertical axis of the theodolite, which you can think of as if passing like this. Somewhere here a line can be thought about. That's the vertical axis about which it is rotating. So we want to ensure it is there. So this optical plummet will help us to center the instrument, even if it is windy condition. It doesn't matter, because it's making use of the just line of sight, all the electromagnetic radiations. Now having seen this, our next some more adjustments which are related to the focusing. What we have achieved so far? Well, our problem was we wanted to measure angle A, B and C, and we arrived at this B. We kept our tripod, and after keeping our tripod we centered it, we leveled it approximately, then we put our theodolite on the tripod, we clamped the theodolite with the tripod, and then we leveled the theodolite, and then we centered the theodolite also using precise centering, using centering head of the tripod. And then once it is finally centered and as well as leveled, we are ready to take the observations, because we have made our horizontal plate to be horizontal, or this lower plate where the graduated ring is, it's horizontal now. Now we can take the observations for the angles. Well, what will be the next step? Next step will be, well, for example, let us say this B point is where I am standing. A is somewhere in this room on that side, and the C is somewhere in this room on this side. So if it is so, what I will do, at A there is something, either a tree or a ranging rod, some object is there which I need to bisect. So I am bisecting now the ranging rod at A. So in order to bisect, what we will do, as we have seen, first we will make use of the target site, because the field of view of the telescope is very small. So making use of the target site, I bisect it. Well, that is bisected. Using the target site, I clamp the lower clamp. The upper one is already clamped. I clamped it. Now it cannot move. Now I look through the telescope. Now when I look through the telescope, I need to see the object very, very clearly. Also, I need to see the crosswire very, very clearly. The crosswire. Because crosswire is the frame. We have seen the crosswire, the utility of that. Because the crosswire as such is somewhere here. The diaphragm is fitted here. The crosswire is fitted here, somewhere here. Now what I need to do, I need to see this crosswire very, very distinctly. Why? Because the image of the objective, we form it on the plane of the crosswire. If I can see the crosswire very distinctly, I will see the image very distinctly. And we need to bisect the object, whether ranging rod or the pole, very, very, with accuracy. So I need to see it distinctly. So the very first step in the focusing is we need to focus for crosswire. And that we also say focusing eyepiece. Now how do we focus the eyepiece? Well, to focus the eyepiece, what we can do, we can make use of a white sheet. I put it in front of the telescope, or you can turn this telescope towards the sky or any white background where we can see the crosswires very distinctly. Well, once it is so, I now focus the eyepiece, and this eyepiece needs to be focused because it will depend upon my eye. So if someone else is working, he will again needs to focus it so that we can see the crosswire very distinctly. Once I have focused this eyepiece for my eyes, so I can see the crosswire very, very distinctly, what will be the next job? The next job will be focusing the objective. Now focusing the objective lens, the meaning in this case is, well, we are looking through the telescope now. The object is somewhere in my field of view. What I will need to do, because so far I had bisected only using the rifle sight, I will need to bisect it more accurately. And before that bisection, I need to focus it. So I will focus using the objective focusing screw. So when I am using it, what is happening? There inside the telescope, an extra lens, which is moving here inside, so that it is ensuring the image which is being formed inside this telescope of the object will finally form on the plane of the crosswire. Because I can see the crosswire distinctly, I will also see the image of the object distinctly now. So this is what is achieved by focusing the objective. That image is formed here in the plane of the crosswire. So I will start seeing now the image very, very distinctly, no fuzziness in that. And at that moment now, I will rotate my tangent screw of the horizontal plate here as per the requirement to bisect that particular ranging rod exactly. So these are the steps. All these steps we need to do: focusing the eyepiece, focusing the objective, and then final bisection. So once I have finally bisected that particular point, I can see the readings here. Okay, what all these readings are. Then I change the upper plate, lower is clamped. We'll talk about that in a moment. Lower is clamped. I change the upper one. Same procedure we need to do for this also. I don't need to focus the eyepiece anymore because it's the same user who is working with the instrument. But I will need to focus for the object because the object distance may be different, shorter or longer than the object at A. So again I focus for this particular object, and then after focusing it, I bisect it very precisely using the tangent screws, and now I am ready to take the readings in these two verniers again, reading A and these two verniers. So what it will give me? It will give me the angle value here. in the horizontal. So this is how we carry out all these temporary adjustments of the instrument. Okay, now we will see how we actually measure the angle. What are the methods of measuring the angles? There is one method which is called method of repetition. First we will see how to measure one angle using this particular method. Basically, well, the job is, as we have been doing always, we have A, B and C. There is a ranging rod or some object at B and C, and there at B we have our survey station. A and C are the ranging rods, and we want to measure the angle A, B and C. We saw just now, this is a simple procedure of taking the observation for this angle ABC by observing the readings on the verniers and taking their difference. But what is special about this method of repetition? So we'll talk about that now. In method of repetition, we try to achieve some extra things. Number one, we increase the precision. What is the meaning of that? The meaning is, if our theodolite is 20-second theodolite, the least count is 20 seconds. We improve the precision. We try to increase this further down, maybe 10 seconds, 5 seconds. That kind of, we increase the precision by this particular method. Number two, we also eliminate some errors which are in the theodolite. We'll talk about these errors in detail later on. But one error, for example, let us say, if this is our graduated circle, if you are talking of the horizontal one, the lower one, that's the lower one, and the graduated circle of this. Now ideally speaking, the graduated circle should be graduated in a very uniform way. Uniform means all these graduations should be equally apart. That means if it is 0, this is 90, this is 180, and this is 270, and so on. And also the graduations in between should be uniform. But if it is not the case, which might be so, because this plate is manufactured somewhere, then in the manufacturing process there were some defects, and because of that, what has happened now, this 90, instead of being here, the 0 is here, the 90 is somewhere here. I am just exaggerating it. But let us say if this is the case, this 180 is here itself. There is no change in the 180. So the meaning is the graduations from 0 to 90 are far apart, they are larger, while the graduations from 90 to 180, they are nearer to each other. So if you are measuring only once, as we did the process here, we bisected our ranging rod A, I took the reading, then I bisected the ranging rod B, or at C, I took the reading. Now if in between we are only observing from 0 to 90 here, what will happen? Let us say the angle which was measured was this. So the actual angle value is, if 21 degrees, what will measure it? We'll observe it in the theodolite slightly less than that. Let's say 20, which is less than 21. Why? Because these graduations are far apart. Similarly, in this part, if we are observing, we will be observing a smaller angle to be larger. So this might happen. So we will try to also, besides increasing the precision in the method of repetition, we can also eliminate a problem like this while we are going for method of repetition. Now how we do it and how we write the readings, right, what we do in that particular process, we'll do it using this particular table here. And before the table, I would like to give you two more definitions. The definition number one is face left observations, and the second is face right. What these terms are? Okay, for me, I am here right now. That's the vertical circle. We know this is the vertical circle. Okay, And if this vertical circle is on my left, and now observations, all the observations which I am taking are called face left observations. How to turn it into face right? I can transit my theodolite. Now for me to take the observations, I will have to bring the eyepiece towards me. So the eyepiece is towards me. Now this face has turned towards my right hand side. So all the angle observations which I will take now are called face right observations. Now it is very clear why we need to do it. We will see later on. There in the theodolite there are many sources of the errors. If you are taking the face right observations, I am measuring couple of angles. Then I change it. I change the face to face right. Then I face left, and now I observe the same angles again. And by taking the mean of those two angles, we can eliminate several errors which are there in the theodolite. So this we will see later on when we are talking about the errors in the theodolite. So right now we will take it like this: face left observations and face right observations. Okay, so the table which I have made here is for face left right now. As you can see here, face left observations. Now what we do in the method of repetition, we will follow it here in the table as well as with the instrument. And please follow each and every step what I am doing. Well, as we had seen, we had to measure the angle A, B and C, and we are at point B. A is there and C is there. Okay, so very first step. Right now you have to follow with me what I am doing. You have to imagine that what is happening in the instrument, because we have already discussed the construction of the instrument. Okay, I clamp the lower one is clamped, I unclamp the upper one. Now I can rotate my instrument. What do you think, the readings are changing or not? If I look through it, yes, they are changing, because what is happening there now, the lower one is clamped, upper one is free to rotate, and if I am rotating my telescope, it rotates like this. So the readings, what the readings are, these in verniers, they are moving on the graduated circle, and we take the reading, we observe, we read the angles against these verniers, because they are moving, so the angle values are changing there. So right now this is lower is clamped, upper is free to rotate, so the readings are changing. Okay, what I do, I change the readings looking through the window here, and I bring it nearly to the 0, 0, 0. What is the meaning? The 0 of vernier and the 0 of main plate, they meet each other. So now at this stage, they nearly meet each other, and I clamp the lower one. Sorry, clamp the upper one. Lower one is already clamped. I have clamped the upper one. Now I look through the eyepiece, I will see a magnified view of the scales here. Then I use the upper tangent. And by using the upper tangent over here, I am using the upper tangent. What I am doing, I am giving very slight movement to the index arm or this verniers, in order to ensure that the reading is exactly 0, 0, 0. Well, the reading is here is 0, 0, 0. This is vernier A and this is vernier B, because there are two verniers, 1, 2. So the reading at A is 0, 0, 0. Over here the reading will be 180. So here the reading is 180, 0, 0, 0. So what I do, my reading now is 180, sorry, 0, 0, 0. When I say 0, 0, 0, I mean 0 degree, 0 minutes and 0 seconds. Now what I am doing, I am releasing the lower one and I take it to my point A. Now point A is bisected. Let us say I have bisected roughly using the rifle sight. I clamp the lower one is clamped. I use the tangent screw of the lower one in order to bisect A correctly. Okay, that is now bisected. Now in this process, because the upper one was already clamped, so these two plates, they move together. So there is no change in the reading. A is bisected, still the reading is 0, 0, 0. So what I do, instrument at, the very first thing here is instrument at, we know we have kept the instrument at B, we have sighted A, sight to A, and the readings at that point were 0, 0, 0, and here this is for vernier A and this is for vernier B. In vernier A and vernier B. In vernier B, we write only in minutes and seconds. So it is 0 and 0. If it is not 0, 0, whatever the readings will be, we will write that. Because there might be some case where it will be so. Why we don't write in degrees? Because generally they will not differ in degrees. If it is 0, it will be 180, generally speaking. So only difference will be in minutes and seconds. So that's why we need to write it this way. And then we can compute the average, which will be 0, 0, 0. Next, now my B is somewhere here. So what I do, I release the upper one. Upper clamp is released and I rotate it to B. What is happening now? In this case, if the upper clamp is released, only the vernier will rotate. While I am rotating this telescope, only the vernier will rotate and the angle value will change. So if this angle is theta, it has moved by theta, I clamp the upper one, then I sighting through the eyepiece, I sight the C, that the C is there, and I use the tangent screw to sight it or bisect it accurately. Now there will be some reading. So this reading will be equal to theta. So I have sighted C and I can write the observations here. But we are doing the repetition, so we will not write the observations. You can record it, of course, there is no problem. So the reading here in the scale at the moment is equal to the angle here. Now what next we do? We release the lower plate. See, the upper one is clamped, I am releasing the lower one. Releasing the lower one means if I rotate now, both these plates will rotate together. And what is the angle value? The angle value is theta. The reading which is being seen here is the theta, because it's not changing anymore. Well, I rotate it, take it back again to the A, clamp the lower one, so the lower one is clamped, bisect the A using the tangent of the lower one, accurately bisect it. Still, I am bisecting A, the reading in my instrument is only theta. Well, next what I do, I release the upper one, then I rotate the upper one, again bring it to C. Now when I am rotating it, the reading value is changing, and once I have bisected C accurately using clamp and the tangent, the reading there in the instrument should be 2 theta. Similarly, if I keep doing it, release the lower one, bisect A, clamp it, the reading is still 2 theta, then I clamp the lower one, release the upper one, bisect C, the reading will become 3 theta. So finally, depending how many repetitions I have done, I write the final value of the angle here. Let's say the final value is 210, 20 and 40. That means 210 degrees, 20 minutes and 40 seconds. And similarly for the other vernier may be 19 and 20. And then I take the average of these two. So the average of these two will reach here, and whatever the average value, I will write that average value here. How many repetitions? Let us say I had done 5 repetitions. So what is the value of the angle? Well, whatever is this total value over here, divided by 5 will give me the horizontal angle. And throughout this process, as you will observe, the face of the instrument is towards my left. We can do the same thing by keeping this face towards my right. Well, what I do now, I change the face is towards my right, and I repeat the same procedure. I make the readings 0, 0, 0, then releasing the lower one, I take it to the A, clamp it, release the upper one, take it to C, and theta, 2 theta, and all this process will be repeated. So what I am doing, mechanically I am adding the angles here. Mechanically, just by using it, theta, 2 theta, 3 theta, 4 theta, 5 theta, I am just doing it, and mechanically I am adding the readings, and that final reading divided by number of the observations, the final reading value divided by how many observations were there gives me the angle value, theta. So we have now from our previous table the angle for face left, and as well as from this table angle value for face right. So finally what we do, we take again we have the angle for face left, face right, and we take the average of these two. We'll talk about this later on, why we need to take the average of face left and face right. So this is the method of repetition. Now it should be obvious to you how we increase the precision, because we are mechanically adding the observations and dividing it by 5 or number of repetitions. So we are in effect increasing the precision. Number 1. Number 2, the same angle. Now here in this case, what we were doing? We were observing the same angle in different parts of the graduated circle.